Okay, so we're going to take a look at the fundamental theorem of calculus, part 2. And we're going to start off with a simple example. But first we're going to define a new function. So we have capital F of x is equal to the integral from a to x of little f of t dt. And what this is called, you can think of this as the cumulative area function. And basically what it does is, let me draw a little picture. Let's say you have a function. Let's say this is f of t. And so let's say, for example, that our point A is right here. What this function does is you'll plug in a number here, for example, 5 or 3 or 7. And what this is going to do is this function is going to find the area from the starting value, which is A, to whatever value you ask it to. So like, for example, if you were to plug in 5, this function would collect the area from A all the way up to 5. But then if you plug in, for example, 7, well then now you're asking it to find the area from A to 7, so it'll collect all of that. So it's basically an area collector. Okay, so that's the way to think about it. Okay, so let me show you an example of what this looks like. And so we have, let's say, for example, you have capital F of x is equal to the integral from 2 to x of, let's do a really simple one, just t dt. And the question is, what is capital F prime of x? So what's the derivative of this function? Because now this is a function. Okay, so the derivative of this function is equal to, well, we need to first find out what this function is. Well, this is easy to find, right? Because we have the first part of the fundamental theorem of calculus, which says, okay, find the antiderivative, which is t squared over 2, and then evaluate it from 2 to x. Okay, so then this is equal to x squared over 2 minus 2 squared over 2. So 2 squared is 4, over 2 is 2. So this right here is capital F of x. Okay, so this is the area collecting function. So hopefully that makes sense. So basically, if you plug in 3 into here, the number that you get is the area underneath t from 2 to 3. If you plug in 4, you would get the area underneath the curve from 2 to 4, and so on and so forth. Okay, so capital F prime of x is equal to, well, that's just the derivative of this, right? So let me just write it longhand. I know this is a simple example, but it's important to go through it. So x squared over 2 minus 2. So the derivative of this is 2x over 2 minus 0, which is equal to x. Okay, now one thing to notice is that right here, the function here, your derivative, is the same as the function that you got the that you were getting the antiderivative of, except for the variable. But that's what basically the fundamental theorem of calculus says. The second part is that if f of x, capital F of x, is continuous on closed interval from a to b, then capital F prime of x, which is the same as saying the derivative of the integral from a to x of f of t dt. So here I just changed the notation. This is equal to little f of x. So if you were going to write this down in two basic steps, basically what this is saying is that if you're getting the derivative of the integral function, then all you need to do is, as long as it has this form, it's going from a constant to x, then you can simply plug in that value x. And so, for example, if I want to find the derivative of, let's say, the integral from 4 to x of t squared dt, what the fundamental theorem of calculus part 2 says is that this is simply equal to x squared. And that's it. And you'll notice if you try, if you find the antiderivative of this function and then find the derivative of it, you'll get this exact same answer, just like we did up above in this first one. Okay, now, so that's good, and we'll do some more examples in a minute. But what I want to do is I want to see if we can conceptualize it. So we want to make sure that we have a conceptual understanding of how this works. And the way I'm going to show you is we're going to use the interpretation of velocity. So let's say we have, let me draw a little picture here. So we have a function, let's call this, this is f of t. And let's think of this function as giving us the velocity over time. Okay. And let's give it a starting value a. So this isn't really a proof, more of an explanation of why this is true and what it's telling you, what the fundamental theorem of calculus is telling you. Okay, so we have our area collecting function, capital F of x is equal to the integral from a to x of f of t dt. Now, in this context, since the vertical axis represents velocity and this function f of t represents the velocity at different points in time, then what this function tells me is it basically, so here at different x values, so x is moving along here, so x can be different values. This is collecting the area underneath the curve, right? But it's changing. So x is a variable, x is changing. But in this context, in the context of velocity and time, remember that the area underneath the curve represents the distance traveled. And we'll see later that, I mean, it's really actually the displacement, but let's just simplify it and call it just distance traveled for now. So, okay, now, this is changing, right? And so this right here, what we're saying is that this function, what it tells us is the distance traveled from time a to x. Okay, so that's the interpretation of this integral function. So as x changes, it'll give you how far you've traveled from a to x. Now, let's interpret this one, capital F prime of x. The interpretation of this is, well, if this is the distance traveled, another way of thinking about it is you can think of it as the position function, right? Because it'll tell you how far you've you've gone based on what x is. So if this is the position, if you get the derivative of that, this is going to represent the velocity at x, right? Because the derivative, remember, is the instantaneous velocity at this point. So the velocity at x, that's what capital F prime is. But the velocity at x, if x is right here, the velocity is right there. It's just that single point, little f of x. So capital F prime of x, the derivative of this is equal to little f at that point x. So it's so simple that it's mind-boggling. So go ahead and rewind and hear that again. This is really important. And then we'll do some examples. Let's do, now you've got the concept down. Okay, so let's do an example of using this. Let's say we want to find the derivative of the integral from 2 to x of sine of t squared dt. Now notice the fundamental theorem of calculus doesn't say you have to find any antiderivatives or anything. It just says that as long as you're going from a constant a, those are the requirements. This has to be a constant, and this one up here has to be a variable. Then the derivative of this is simply the inside function evaluated at that variable, x squared. And that's it. You're done. That's it. Now, of course, it's too easy, right? Can't be that easy all the time. Well, there are some snafus. Can get a little more challenging. Let's say, for example, you have the derivative of the integral from x to 4 of tangent of t dt. This isn't in the form, right? Well, can you put it in the form where it has constant on the bottom, variable on top? Why, yes, you can, using one of your properties of integrals that you all remember, of course. You would have the integral from 4 to x as long as you flip the sign on the outside. So this is equal to negative the integral from 4 to x of tangent of t dt. And now that you're going from a constant to a variable, x, this is simply equal to tangent of x negative tangent of x. And that's it. That is it. Okay. Now you're thinking, well, no, it can't be that easy. Well, you're kind of right. Because we can make it more crazy. Craziness can abound. Let's say you have the integral and you have a constant on the bottom, but let's say, for example, you have you're going from 4 to x squared instead. Now, let me do some. Okay, so the integral from 4 to x squared of e to the t minus sine of t dt. Okay, so that's great. Good times. So now notice that the fundamental theorem of calculus doesn't say anything about having, actual functions up here. I mean, if you're going from a constant to x, that's okay, but not from a constant to x squared or from a constant to, sine of x or, some kind of function. So this is a bit odd, but remember that what did you do when you were finding the derivative of a function of a function? Do you remember? You had to use the chain rule. So going back to the derivative stuff that we did way back in, that 2 chapters ago, This right here would correspond to the inside part of your function, because you're basically, this is a composition of this function. I won't write it down, but this, you're plugging x squared inside of this spot right here, which is normally just x. So, you know, you might think, oh no, this is going to be crazy, but it's not really that bad, because you follow the same logic. So remember that when you use the chain rule, it says, okay, get the derivative of the outside. So the outside here is the entire integral function. So the derivative of the outside, you use the fundamental theorem of calculus, which says, okay, plug it in to all of the t's. And so you go, okay, so you would have e to the x squared minus sine of x squared, right? Okay, now that's the derivative of the outside, and then notice you're leaving the inside alone. This x squared, that's the inside. And so then after that, you're going to multiply by the derivative of the inside, which is simply 2x. So this right here, this is the derivative of the outside, leaving the inside alone, and then this is the derivative of the inside. So I know that it takes a little while to sink in, but go through it a couple times and it'll make sense. Let's do another one. Let's say we want to find the derivative of the integral. Let's get really crazy. Like, let's go from I don't know, how about cosine of x to the fourth to tangent of x squared. All right, so I'll admit this one's getting pretty crazy. I'll admit it. And let's make the inside t to the fourth minus 3t dt. I didn't want to make that the inside part of the function that bad, because otherwise it won't fit on our on the space that we have. Okay. All right. Now, how can we possibly deal with this terrible situation? First off, we're not going from a constant to a function here, or a constant to a variable. We're going from a function to another function. But we can bring out one of the other properties of integrals that we had, that basically says you can split it up, whack, right there at some value. Now the value that you split it up at, it doesn't really matter. You can use you can just use a generic constant c, or you can use 0. Sometimes I just use 0. It doesn't really matter. I mean, remember, it's basically you have an integral going from two values, and so you're just splitting it up at the same part, and then you just add both of them separately. So you would still get the same thing. So let's split this up. Let's go the integral of cosine of x to the fourth to some value c. Let me use green for this one. And then we're leaving all this stuff alone, minus 3t. So we're not using the fundamental theorem of calculus yet. We're just splitting this integral up. And then plus the integral from c to tangent of x squared of t to the fourth minus 3t dt. Okay, now notice all we did is, the way to think about this is, think of this as almost like a number line going from this value right here to this one. And so if you've got a number line, basically what you're doing is you're saying, okay, where I'm going to start right here, and then I'm going to go to this spot. So that's this first integral. And then this one is going to start at this spot, and then I'm going to go up to the end, which is tangent. So that's all you really did. All right. And so then notice that this second one is in the form that I want, but this one isn't. because the constant is on top instead of on the bottom. But that's an easy fix, right? Because you just put the negative sign on the outside, and you just flip the inequalities, flip the limits of integration. So let me go. Okay, so I'm going from negative, from c to cosine of x to the fourth. Boom. Done. Okay. Now off to use the fundamental theorem of calculus. Now I'm running out of room here, so I'm going to try to do the best I can. Okay, ready. The derivative of this first one. So you have, ooh, yellow's too bright. Okay, you have the derivative of the outside with the minus sign there, which just says, okay, plug in this. That's what the fundamental theorem of calculus says. Plug in this function inside of the t's. Okay, so that means that you're going to have minus, well, hopefully this fits, cosine of x to the fourth all to the fourth minus 3 cosine of x to the fourth, another parentheses. Okay, so that's the first part of the fundamental theorem of calculus, right? Okay, and then times the derivative of the inside, times the derivative of cosine of x to the fourth. So the derivative of cosine of x to the fourth is negative sine of x to the fourth. What did I get myself into? Times 4x to the third. Whoa, craziness, craziness, craziness. Okay, now for the next one, the same exact thing. You're going from a constant to tangent, so we're going to use the chain rule. And so the first part says plug in tangent of x squared inside each one of these. So I can do that. So I have plus tangent to the fourth of x squared minus, I'm going to have to leave this, minus 3 tangent of x squared. Okay, so that's what I get when I plug in tangent of x squared inside of the t's, and then I'm going to multiply times the derivative of the inside. So the derivative of tangent of x squared is secant squared of x squared times 2x. Whoa. It left. What happened? Oh no. Left the screen. Sorry. Okay, there it is. I'm back. And that's it. That's the answer. I can't even box it. It's so massive. There it is. There we go. Nice work, guys and gals. Nice work. That's the derivative of that function.